Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asghar, and today the topic of our discussion is synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. In our previous lecture, we have studied about the microwave synthesis of inorganic compounds, and in this lecture we are going to study about intercalation and deintercalation. A very elegant way to synthesize new material is to take an existing crystalline solid and either introduce new atoms into the empty spaces sides or selectively remove certain atoms. This is supposed to be one of the most elegant way for the synthesis of new inorganic materials. In this synthesis, we have to uh, introduce some of the new atoms in the some of the interstices, empty spaces, or you can say the empty sites, and or we have to remove some of the selective atoms from that certain crystalline compound. That would be the elegant way to synthesize materials while keeping the overall original structure intact. This would be the most important thing in this intercalation and deintercalation. These are some examples of topotactic or topochemical reactions in which there is a strong three-dimensional similarity in the structures of starting phase. That would be the host structure and the product. Intercalation guest or species can either be ions or molecules. For intercalation and deintercalation reactions that involve addition or removal of ions. The removal of ions, which the common ions are actually lithium, sodium, H positive, and oxygen, O2 negative. For intercalation and deintercalation reactions that involve addition of these ions, electrons must also be added or removed to preserve charge balance. There are therefore solid state redox processes and an automatic requirement is that the host material should be a mixed conductor so as to allow the migration of both ions and electrons. With certain host structures, it is also possible to intercalate organic molecules and even fairly large polymers. Most intercalation hosts are layered structures with strong interlayer bonds but weak interlayer bonds. It is actually most intercalation hosts are layered structures with strong intralayer bonds and weak interlayer bonds. Guest species intercalate and the empty space between the layers and push them apart. There are examples of three-dimensional guest species intercalate the empty space between the layers and push them apart. There are examples of three-dimensional intercalation host, but in this case there is a very little volume change on intercalation, which places a strict limit on the size, often small, of the species that may be intercalation guest. Some examples are actually shown in this table. Here we can see that host is graphite, titanium sulfide, zirconium selenide, and the guest would be the potassium bromine molecule, iron chloride FeCl3, lithium, ammonia NH3, and amines. While the comments on the whole intercalation is stacking occurs to give KC8, KC24, etc., while lithium X TiS2 was an early prototype lithium battery cathode. Most lithium cathodes are intercalation compound. The second is NiPs3, VPSE3, MOO3, and B2O5, while the guest one is cobalt, osine, COCP2H, Na, sodium. The comments is molybdenum and vanadium bronze color changes find electrochromic applications. The host is FeOCl ZrHPO4 twice kaolin. The guest is ferrocene FeCP2. Organic molecules aluminate anions. Examples of a pillared clay on heating. While anatase TiO2, the guest would be Li lithium. The comments on this host and guest is transforms to LiTi2O4 spinel superconductor on heating, while host is MO6X. X would be any sulfur, selenium, tellurium, or YBA2CU3O6. The guest is lithium oxygen. Several phases, some are superconducting, while alkali metal interaction can be carried out. Number A. A is electrochemically using salts such as lithium polyethylene oxide plus LiClO4 TiS2, or Na propylene carbonate plus Ni NaI NBSE2. The B is in these cases the electrolytes are non-aqueous solvents of either organic liquids such as propylene carbonate or polymers containing polar functional groups such as polyethylene oxide, into which are dissolved alkali metal salts easily. The B is chemically XC4H9 LiTiS2 is equal to LiXTiS2 C18, C8H18. An example of an intercalation reaction that has to be mentioned because of the incredible change in properties that occurs in the topotactic conversion of anatase polymorph of TiO2. TiO2 is a white insulating solid to a lithium titanate superconductor. The first step is to react anatase with N-butyl lithium dissolved in hexane. Lithium plus ion and electrons inter- intercalate into the anatase structure, which has open ID channels or one-dimensional channels, not like unlike those in rutile. No significant structural change occurs on intercalation of lithium. The second step is to heat the lithiated anatase LIX-TiO2 to 500 degrees Celsius. This causes structural reorganization and gives a material with same composition but with spinal structure and which is superconducting with a transition temperature or Curie temperature of 13 Kelvin. This insulator to superconductor transformation is almost as miraculous as to fishes to birds transformation, which we have discussed earlier. The reaction the reaction that take place may be summarized as under: a TiO2 anatase plus Xc4H9 lithium Li change into LiX TiO2 plus XO2C8 18 octane. LiX TiO2 lithiated anatase then at about 500 degrees Celsius change into LiX TiO2 spinal. N-butyl lithium is a powerful lithiating agent which effectively it is a source of atomic lithium. A useful dilithiating agent is iodine I2 dissolved in acetonitrile CH3CN, which actually gives the reaction like this: LiCOO2 plus I2 which is in acetonitrile and change into LiXCOO2 plus lithium iodide CH3CN. Products with a large range of X values are obtained by controlling the amount of iodine used. The driving force is the formation of lithium iodide, which is soluble in CH3CN. The next one is the graphite intercalation compounds. Graphite is a classical example of host crystal capable of intercalating a wide variety of atoms, ions, and molecules. Graphite has a planar ring structure as shown in this figure A. It is possible to intercalate alkali metal cations, halide anions, ammonia and amines, oxysalts, and metal halides between the carbon layers. The structure of graphite is a kind of projection showing the two layer stacking sequence, and the graphite potassium in B. The graphite layers are superposed in projection, but the potassium atoms are not, and various stacking sequences are possible. Structure B is actually the typical donor and acceptor complexes of graphite. Graphite is actually the allotrope of carbon, which forms the hexagonal structure, and it have layered structure, while the distance between the two layers is about 3.35 angstrom, while the distance between the two consecutive carbon atoms in a same layer is about 1.41 angstrom. Some typical reactions and conditions for formation of graphite intercalation compounds are here, in which graphite in the presence of HF and fluorine at about 25 degrees Celsius change into graphite fluoride, which is black in color, and C3.6F2C4F, while graphite in the presence of HFF2 at high temperature about 450 degrees Celsius change into graphite fluoride, which is a white powder, and change CF.6A to CF. And graphite in the presence of potassium melt or vapor state change into bronze, which is carbon 8 potassium C8K. C8K, while partial vacuum, the presence of partial vacuum change into steel blue, which is C24K, and C24K subsequently into C36K, which is then C48K, and rest is changed into C60K. Potassium uh, graphite somehow react with the sulfuric acid concentrated and change into C24 plus HSO4 minus with 2H2SO4 and hydrogen gas, while graphite with iron chloride FeCl3 change into graphite FeCl3 intercalate, while graphite with bromine water change into C8Br. Most of these reactions are reversible in nature. It means that if a reaction goes upward and change into products, then it have subsequently change into reactants by reacting the products. Thus, C8K, which is bronze, forms an own exposure of graphite to the molten potassium, which may be subsequently removed in stages under high vacuum. These reactions are reversible because the structure and planarity of the carbon layers are essentially unaffected by intercalation. The actually structure of this graphite, the carbon atom in graphite is actually quite important for these kind of reversible reactions, because the uh, carbon atoms in this hexagonal structure arrange themselves in such a way that every carbon atom is attached to the three nearest carbon atoms and maintain a distance of 1.41 angstrom, while the layer distance between the carbon atom is 3.35 angstrom. And this uniformity of in graphite actually the reason of reversible nature of reactions, and are somehow essential unaffected by intercalation. The structure and electronic properties of graphite are already described. Here we note that the bonding within the graphite layer is quite strong, with an average carbon-carbon bond strength of 1.5. But adjacent layers are held together by weak van der Waals bonds, as evidenced by the relatively large interlayer spacing of 3.35 angstrom, which is shown in this picture A. This weak bonding permits foreign species to intercalate between the layers, and it is also possible to push them apart too. For example, this is actually the standard distance between the layers of graphite molecule, which is 3.35 angstrom. But somehow some invaders or doping materials actually uh, have ability to push these layers apart from each other, which actually change the normal distance, which is 3.35, and may change to 3.4, 3.7, or sometime 5.5. Herein I would like to give an example in which the layer distance pushed to 5.5 angstrom in C4F, while approximately 6.5 angstrom in CF, while 5.4 angstrom in C8K. The structure of the intercalation compounds are often not known with certainty. The probable structure of one C8K is shown in this diagram B. The relative positions of carbon layers are different to those in pure graphite, as they form a AAA stacking sequence. Potassium ions are somehow looks like sandwiched between the pairs of carbon rings, giving potassium ion a coordination number of 12. If all such sites were occupied, the stoichiometry C2M would result, but in C8K only one quarter are occupied in an ordered fashion. The electronic structure of graphite is modified on intercalation of potassium, since partial electron transfer from potassium to graphite occurs. It would actually result in a polar structure, which may be represented as C8 minus K positive, and this is all about the intercalation compounds and intercalation in graphites. Thank you very much.